Hi everyone and welcome to my YouTube channel. In this video, we'll be discussing the 2024 USEMO, that is the United States Ersatz Math Olympiad of this year. So, like a quick introduction for this Math Olympiad. Basically, this contest is organized by Evan Chen. The problems are proposed by different people, and everything is done online. So the whole test is done online. It's basically the it's targeting the US students. They participate online through the AOPS, that is the Art of Problem Solving platform, and even the grading happens online. So I happen to help in the grading of the 2023 actually USEMO, and like was supposed to also help in the 2024. Unfortunately, I was busy, and like when I was available, all the papers were already graded. Anyway, in this video, we'll be starting with problem 1 of this contest. As you can see, this contest is similar to the IMO style. Like we just have day 1, day 2. Each one of them has 3 problems, and we are given 4 hours and a half for each day. So in this video, we'll be discussing the first problem of day 1. Yeah, so before you start with the video, don't forget to like, share, and subscribe to the channel. And what are we waiting for? Let's get started. Alright, so problem 1 is a combinatorical question. As you can see, we have 1001 stacks of coins, S1, S2 till S1001, and each stack, Sk, has k coins. And like the process that we can do each time is choosing a pair ij, such that I is less than j, with the following 2 conditions. Si and Sj should have at least 1 coin, each one of them, and the ordered pair ij must not have been selected before. So we can select each pair only once, at most once. Okay, so if we follow these 2 conditions, then we can do the following process. If Si has like A coins and Sj has B coins, then we can subtract the GCD of these 2 numbers from each, both of them, from Si and Sj. And we're asked to try to maximize the number of times this operation is performed. Okay, so this is a maximization question, kind of standard combinatorical question. So let's start. First of all, let's see what exactly is the process telling us to understand it better. So let's say we choose a pair, some pair, and this pair has like A and B. Then what we are doing is we're subtracting the GCD from both of them. So now A is A minus D, and B is B minus D, where D is the GCD, of course, of A and B. As you know, this is like the GCD, symbol. Maybe I should right now say just GCD, not to confuse you with the pair. Okay, so something like this. Okay, so if we start with AB, we're subtracting the GCD from both of them. And our goal is to try to maximize the number of times we can do this, because each time, of course, we're decreasing both of the numbers. But as you know, for example, if you apply this on, let's say, 10 and 5, then what will happen is this will become 5 and this will become 0. So quickly, 5 became 0, and 10 has dropped by, let's say, a half. However, if you do it like 10 and 9, then this thing is just going to be 9 and 8, which is kind of close to this. So surely our goal should be to try to do something like this, right? We want the GCD to be as small as possible. Perhaps the best case is to try to choose coprime numbers. If we choose coprime numbers, then we can just subtract by 1. So now instead of making it A minus D, A, B minus D, if we choose D to be 1, then we'll just be going A minus 1, B minus 1. So for sure, when we're trying to build our example, we should try to do something like this. Okay, so that was like a good analysis. We should be trying to pair some numbers that are co-prime. Okay, so let's give it a try. So we can go from 1 till 1001. We have these numbers at first. Actually, let's generalize, because clearly like 1001 is not really that much special. We can just like denote to this like by n, and keep in mind maybe that n is odd. Perhaps we might need the odd thing. N is odd. Okay, so what is our goal, or what is our strategy? What should we try to do? As we said, our goal is to try to pair co-prime numbers. How can we like pair co-prime numbers? How can we guarantee that two numbers are co-prime? Because if we choose like randomly, we don't really know how to do that. The easiest strategy is just to try to go for maybe consecutive numbers, right? So maybe like if you pair 1, 2, 3, 4, something like that, n minus 1. These are co-prime numbers. So when we apply the strategy, this is like going to be good. However, like, should we immediately like try going pairing everything, or should we just try to catch a number and see? Like maybe just catch the maximum number and just try to decrease it step by step, because of course we can apply the operation many times, right? We can catch, for example, this number and try to apply it like many times, and then once we're like done with it, we try to catch the other number, and so on. Perhaps like this is a better strategy to get rid of the like big numbers, right? So let's try to do that. So first of all, we're going to catch n with n minus 1 and apply the like this process. What will happen is the following. These are still the same. Now we have n minus 2. N minus 1 has become n minus 2, and n itself has become n minus 1. Okay, we've done the process once right now. What next? This number, what can we do next? Now we cannot do this anymore because we have used this once, but what we can do is just simply do this, right? These are still co-prime, so perhaps this is a good idea to do it. So let's try to do that. So now we have n minus 3, and this thing has become n minus 3. This thing is n minus 2. This thing has become now n minus 2. Okay, now what can we do? This is now broken. We cannot do this, neither this, but we can do this. So simply we can just like do this again. And as you can see, we can actually keep doing this again and again and again till like the end. We can actually do it with 1 itself, right? If we keep doing this at the end, this is going like what exactly is going to happen? As you can see, the numbers are decreasing, right? So this thing has become n minus 2. This has become n minus 3. This has become n minus 4, and so on. Each number is being subtracted. So the 3 has become 2. The 2 has become 1. And when we do it with 1, it's going to become 0. Because like at the beginning we had n. Here how many numbers we have? N minus 1. So each time we're subtracting 1, 1, 1, 1. N minus 1 times. So this eventually will become 1. So that means at the end we're just going to have the following. We have now 0, 1, 2, and so on till n minus 2 consecutive numbers. And we have like the number 1. Okay, now of course this number like we can ignore it because we cannot do this anymore because we've like consumed all of the edges, right? If you like think about this as like some graph and these as edges, like these are all the possible edges, right, from this vertex here. So we cannot do it anymore. Okay, very good. Like getting 1 is kind of good. Of course, like we prefer to get 0, but yeah, this is the best we can do. Okay, so now what we should do is try to catch this number here. Remember, we're trying to get rid of the like big numbers first because they are probably the most difficult to handle. So now let's do it for this thing. Of course, the strategy is the same. We can catch this with this, and it will become like exactly the same strategy. In fact, we are now solving the question just from 1 till n minus 2, right? So exactly the same. Right now here, how many steps we've done? How many operations did we do? If you think about it, we started from n, keep subtracting once, n minus 1 times. right? In n minus 1 times. So we've done the operation n minus 1 times. Now for n minus 2, we're going to do what exactly? Exactly the same, right? So we'll keep doing this how many times? From here to here. It's n minus 3 times. And eventually it will become 1 as well. So if we keep doing this, it's going to become 0, 0, 1, 2. This thing is going to become 1, 1. This is going to become n minus 4, of course. Okay, so how many times have we done this now? It's actually, as we said, n minus 3. Okay, you can see probably what we're doing. We'll be doing this again and again and again till like we cannot do it anymore. When exactly will this happen? If you try to think about it, like we're going to just now add the numbers. This will be our answer: n minus 1 plus n minus 3, and so on. But till what exactly? So if you remember, n is odd, so we're just going over like even stuff, right? Even plus even, and we're going down. And at the end, we'll just be reaching, of course, 2 plus 0, right? In fact, like at the end, this will be just each time you can see that, right? Like 0 here, 1 here, 0 here, 1 here. And because the number of numbers is odd, at the end, like we're just going to have a bunch of zeros and bunch of ones here. And the number in the middle, actually, it will become like it will be just 1. So you can easily just see that we can actually keep doing this till we get 0. So basically, like our answer here is just the number of operations, let's say, is just n minus 1 plus n minus 2, n minus 3, and so on till plus 2 plus 0. So we're just like adding the even numbers, right? Like n minus 1 correspond, as we said, to like the first number. N minus 3 corresponds to the second number, after handling the first number, and so on. This number will be like 0 because it cannot like take anything else. So yeah, this is our answer. We can now just calculate this easily. It's just like the something like this: n minus 1 arithmetic progression. Yeah, you can take 2 as a common factor and get just like a sum of consecutive numbers from 1 till n minus 1 divided by 2. And of course, this thing is just n minus 1 over 2 times n plus 1 over 4. So the 2 cancels the 4, and we just get n minus 1 times n plus 1 divided by 4. Okay, in this case, of course, like this is the answer. In our case, it was 1001 minus 1 times 1001 plus 1 divided by 4. So it's basically 1000 times 1002 divided by 4. That's just like 5000 times 5001. Yeah, so basically this is our answer. Okay. Of course, right now this is what we think is the best way, like the maximum. We just provided we just guessed that this is the answer, and provided an example for it. If we apply this algorithm, then we can get this answer. Now we're not done yet. Now, in fact, we just need to show that this is indeed the maximum, right? Remember, always in these types of questions, you need to do 2 tasks. Number 1, provide like an example for the number that you guessed is the answer. And number 2, show that indeed it is the maximum or minimum or whatever. So here now we just need to show that we cannot get a better number of operations, like a bigger basically. So let's try to do that. Here we're just going to bound the number of operations from above. Okay, so now the bounding argument. Okay, how exactly are we going to bound? Let's write the numbers again. Till n. Okay, so like just as we explained, we're just going to have pairs, right? Each 2 numbers going to be paired. So this pair is like, let's say this edge is the thing that we need to bound, the total number of edges possible we can build right now. So how exactly can we pair these? Okay, we have actually very easy ways to bound these. For example, if you look at any number, let's say maybe like number 3, how many times can we, how many edges can we build from it? Well, of course, we cannot have more than 3, right? Because once we do let's say this became 2, we do this became 1, we do something else, it became 0. Once it's 0, we cannot do it anymore. So that means for any number, kind of di is less than or equal to I, right? Where d is the degree of this, if we imagine this as like a graph. So yeah, we can we have actually this is like a very cool way to bound. So maybe you might think right now we can just put sigma di, sum of di, and just say it's less than sum of I, and this is like our answer. But in fact, this is clearly wrong, because this thing is not we cannot actually get it. It's too bad approximation, because if you take a look at n, for example, can we really get this equality, like di equals or dn equals n? Well, look at n, how many edges it can have. As you can see, we have here n minus 1 number, right? So can it really have n number, n edges? Clearly no. So while this worked for here, yes, we can do it. From the above, we cannot really apply this. The equality case is not respected here. So you should always be careful and respect the equality case, of course. So this thing is wrong. We cannot just depend on this, basically. Okay, so what exactly can we do? How can we bound these? Well, if you look at our example, what we did here. First, what we did, we code this thing and we kept building everything till it became 1, right? And now the numbers here, 0, 1, 2, and so on. So what happened actually, the thing that di is less than I, the equality, actually, where did it happen? It happened only for here, this number. Here, of course, it didn't happen. Same thing here, it happened for this number. It happened for the other number as well. So number 1, how many times we built an edge for it? Once, 2, twice, 3 times, and so on. We can see that the first half, indeed, di equals I for all of them. But for the other, it's not. So maybe we can bound the first half first, and then think about the rest. So maybe this is a good idea. So let's simply just do that. So okay, we have the numbers 1, 2, 3 till n. We want to only take the first half. Of course, we know that any in total is odd. So we just take the first half, that is from 1 till n minus 1 divided by 2. Each one of them, we're going to apply di is less than I. So that means here, let's say the degree of this, it's of course going to be less than the sum of all of these, 1 plus 2 plus 3 and so on. And that is basically going to be, let's evaluate this. It's going to be n minus 1 divided by 2 times n plus 1 divided by 4. Yeah, that's it. Okay, now these counts what exactly? These, of course, counts all the edges that come to these numbers. It's we have these two sets now. First one is the small numbers, 3 till n minus 1 over 2, and the second is n plus 1 over 2, and so on till n itself. So right now what we bounded is everything that come to this. So all the edges either between these, like maybe between 1 and 2, 2 and 3, and so on, and even like the ones that come like these. So these in total are at most n minus 1 times n plus 1 all over 8. Nice. Now what we need to bound is these guys, just like between themselves. We don't need to do this. Okay, so how to bound these? Of course, as we said, we will not now use this anymore, the I less than I. Here, actually, if you try to think about it, if you just like have how many numbers here, from n plus 1 over 2 till n, you actually have n plus 1 over 2. Yeah. If you have n plus 1 over 2 numbers, like how many edges at most you can build between them? Well, if you just like do like connect everything, right? If you connect everything, all the edges possible, then you can just get like chooses 2, n plus 1 over 2 chooses 2. So you can do this. That's equal to all divided by 2. So it's like by 4. Or that's like everything divided by 8. Okay, so this counts, like this bounds all of these between them, like these. Okay, so in total, our bound right now, it's this plus this. And that's, of course, double, because these two numbers are equal. So we get just double that number. And hence, we just get n minus 1 times n plus 1 divided by 4. And indeed, this is our answer, actually. See? And that means, indeed, our bounding was correct. And yeah, that's it. We're done. So basically, like this question was really like not difficult at all. What we just did is we started analyzing the process. We noticed that we just want to try to do like coprime numbers. The GCD is 1 as like much as possible. And then we just try to build this example, getting rid of the biggest number step by step, using everything, all pairs possible, and so on. We just found the answer using this example. It was very easy to find. That was it. And then, to show that this is the maximal, we needed to bound. How do we bound? We can use this. But this one is like not good for all of them. So instead what we did is we remembered that we just applied this actually for half of them. It's correct for half of them. So we just applied this bounding technique for only the first half. And this already like did all of that. The second half was like really a piece of cake. It's just like chooses 2. We used all the edges possible. And indeed we killed the question easily. Alright, so that was probably a nice and easy like combi question. So as a summary, problem 1 was kind of an easy combinatorial question. Basically, the idea was, first of all, we try to analyze our like process, what we know, our operation. We basically want to choose coprime numbers, so we want to pick D to be 1. This is exactly what we try to do. We followed a greedy algorithm of picking the greatest number, and each time we're just like trying to use as much as possible, decrease it as much as possible. And we did the same for all the other numbers as well. So a very like a greedy algorithm. And indeed, it gave us the following answer, this answer. And then we tried to bound, of course. In the bounding process, we just used this inequality, but we didn't use it for everything. We only used it for the first group, the first half. We used this one. But then for this one, we just used basically the dump, like we just did a kind of connected graph. We connected all the edges, and we just chooses 2. And indeed, we just got what we want. Alright, so that was problem 1 of day 1. Let me know, you guys, what you think about this question in the comments below. And don't forget to like, share, and subscribe to the channel, and join the Discord server, where we are posting other papers as well, and discussing tons of stuff there. And see you guys in the video for problem 2. See you.